Hi students, very good morning. Today we are going to learn about field of an electric dipole. So in the previous sessions you have already learned what an electric dipole is. So today we will learn what is the electric field strength at any point due to an electric dipole. So first of all, let me just brief you once again what an electric dipole is, and then we'll get back to the actual topic. So an electric dipole is a combination of two charges. So by definition, an electric dipole consists of two equal and opposite point charges separated by a very small distance. Say plus q and minus q are the 2 point charges separated by a very small distance, say 2a. The center of the dipole, I'll mark it as O here. Then O to one of the charges is distance a. Then a dipole has a characteristic called dipole moment. The dipole moment of a dipole is denoted by vector p, and it is in magnitude equal to magnitude of one of the charges into the distance between them, and of course a unit vector small p which denotes the direction. So or I can say this is equal to 2qa into p. This is an electric dipole moment. Electric dipole moment. What is the direction of the dipole moment? By definition, this cap minus the p vector p cap is a direction from minus q to plus q. So p is from minus q to plus q. This you have learned in the previous sessions. So today we are going to discuss the field of this electric dipole. So you already know that electric field at any point due to a point charge. How to find out that you know. So now here is a combination of two charges, minus q and plus q. We will find the electric field due to these two charges. Now there are different possibilities. So where you want to find the electric field? At any point around, if I say, it is a bit complicated here. So easiest to find is when the point lies either on the axis of this dipole, that is on the axial line, anywhere along this line, or when the point is on the equatorial line, on the bisector of this dipole, that is perpendicular to this axis. So at any point along the equatorial line, also you can find the electric field very easily. So in the syllabus we have these two topics, that is electric field on the axial line and also electric field on the equatorial line. So let us take one by one and try to find out the field strength. So first I'll start with, so of course the topic is field of an electric dipole. So in that I'll take the first case. Electric field on the axis of a dipole. So as I said, dipole consists of 2 point charges. So let me take 2 point charges here and try to find out the electric field. Say there is a electric dipole constituted by 2 point charges, plus q and minus q, and the center of the dipole, say O. The distance between the two charges, of course, that is 2a. At some point P, I want to find the electric field, and that point P is on the axial line, I said. So where is that axial line? Axial line is the line joining the two charges here, that is the dipole length. Then you want to find the electric field due to these 2 point charges at that point and take the vector sum of those two fields to get the net field due to this electric dipole. Now how to find the electric field for each point charge? Let us just check that. So let me consider first of all a point P on the axis. Stop. So to start with, let us find out the electric field due to an electric dipole on its axial line. So the first topic, electric field on the axial line. So let me just consider an electric dipole. Plus Q, minus Q are the two charges. The center is O. The distance between the two charges is 2a, as I already explained you that. Now let me consider a point P on the axial line. So I will say the point P is somewhere here, where you want to find the electric field due to this dipole. The distance to this point P, I will take from the center to be r. From the center of the dipole to the point P, the distance is r. Now you can tell me what is the distance of this point P from Q. From Q, it is totally this much is r, and the half length of the dipole is a. So r minus a is the distance from positive charge. And what is the distance from the negative charge? Of course, this total distance, which is r plus a, because here to here it is r, from here to here it is half dipole length, which is a. So r plus a. Now at this point P, what is the electric field? Now first of all, due to this plus charge, positive Q, the electric field here is away from the charge, which is, I will call E plus Q. And due to the negative charge minus Q, the field here is towards the charge, which is E minus Q. You must have noted I have drawn the length of E plus Q to be more compared to that of E minus Q. The vector length here is more and here it is less. The reason is very simple. The point P is close to plus Q, whereas away from minus Q. So automatically the plus charge will have more strength here, that is this, compared to the negative charge, which is less strength. And the directions, of course, due to a positive charge, electric field is always away from it, and due to a negative charge, electric field is always towards it. Now what is the net electric field here at point P? Of course, E plus Q plus E minus Q, which is the vector sum of these two electric fields. Now let us find out first what is E plus Q and then E minus Q, and then we will add up to get the total field. So for that, let's say you have E plus Q, the electric field due to positive charge. E plus Q is equal to, what is E plus Q? Electric field by definition, by Coulomb's law. The definition of Coulomb's law says electric field is 1 by 4 pi epsilon naught into Q by R square. That is the general definition. So whereas here 1 by 4 pi epsilon naught, what is the charge here? Q. What is the distance of the charge? from P, which is R minus A. So R minus A whole square. So this is the direction of, magnitude of electric field. What is the direction of this? Direction of the field is towards left, which is same as minus Q to plus Q. Means it is same as the dipole moment. Already explained you, dipole moment is always in the direction minus Q to plus Q. So electric field is also in the same direction. Therefore, I will denote it by a P cap. Because direction of dipole moment is in this way. Direction of dipole moment is minus Q to plus Q, and E plus Q is in the same direction as that of P. Therefore, I will call it as P cap there. So this is a vector now. Q is the magnitude of charge plus Q. Now, what is the electric field? Same way, what is the electric field? E minus Q due to the charge minus Q here. So that is E minus Q, which is equal to 1 by 4 pi epsilon naught, the charge magnitude divided by R plus A whole square P cap. Is it fine? Something is missing. That is direction. What is the direction of E minus Q? To the right. What is the direction of dipole moment? To the left. So E minus Q is opposite to P. Therefore, I will put a minus sign with P cap, or I can put the minus sign anywhere here. So I will say minus here, or with the minus Q, doesn't matter anyways. Now, what is the net field? This is field due to plus Q, and this is field due to minus Q. Now, coming to the net field. Net electric field at P. Net electric field at point P due to the complete dipole, that is plus Q and minus Q together. That is given by E is equal to E plus Q plus E minus Q, of course, with the vectors. And you can already guess what is the direction of this E also, because E plus Q is bigger, magnitude wise bigger, and compared to E minus Q. Therefore, of course, the result should be in the direction of E plus Q itself, which is same as that of P. So that you understood. But anyways, let's just find out from the equation here. Now let us add up E plus Q and E minus Q. E plus Q is here, E minus Q is here. What are the common factors here? 1 by 4 pi epsilon naught Q. The whole thing is common. So I will take Q divided by 4 pi epsilon naught as a common factor, and 1 by R minus A square, and here minus 1 by R plus A square. So 1 by R minus A square, then minus sign is there here, therefore minus 1 divided by R plus A square into P cap. So this is the net field. Now let us take the LCM of these two. So the product of these two is the LCM, that is R minus A whole square and R plus A whole square. So which will be, let me just remove this. I'll remove this also. So the net field is so much. So let us just take the LCM of these two and get the resultant. So therefore, E is equal to Q divided by 4 pi epsilon naught into, what is the LCM? See, this is like keeping square aside, R minus A into R plus A is R square minus A square, then whole square, of course. So the LCM is R square minus A square whole square, and whereas on the top here r plus a whole square minus r minus a whole square. You know how to take the LCM. R plus a whole square minus r minus a whole square. So r plus a whole square minus r minus a whole square into p cap. This is the resultant. So which is nothing but equal to q divided by 4 pi epsilon naught into. Now let us just simplify that further. So this is r square plus a square plus 2 ra. This is r square. Okay, let me just write it. R square plus a square plus 2 ra minus r square plus a square minus 2ra divided by r square minus a square whole square into p cap. Now let me just remove this. Now, of course, say r square minus r square cancels, a square minus of a square cancels, plus 2ra minus of minus plus 2ra, which is 4ra. So let me just put that here. Q divided by 4 pi epsilon naught into 4ra divided by r square minus a square whole square. So into, of course, p cap. This is E. Now this is the net field. Okay. Now, as I already told you, as you already know, in the previous sessions also have learned, what is the electric dipole's length of the electric dipole is very, very, very small. So it is almost negligible, I can say. So when you have an electric dipole, plus q minus q, something like that, two charges separated by small distance, and you are finding the electric field at some point p. So usually the distance of p, that is r, is very much greater than the length 2a or the half length a. So r is always practically very much larger in magnitude than a. So assuming that situation, if I just consider here, if r, the distance of p from the center of the dipole, is very much greater than a, which is the half length of dipole, then if r is very much greater than a, then of course a is negligible. So r square whole square, which is r to the power 4. So automatically you find E is equal to, one r gets cancelled here, r square whole square, that is r power 4, one r gets cancelled, so r cube is left out in the denominator. Numerator 4a is there, and there is one q here. So what will it be? 4qa. 4qa. Then what is there in the bracket here? 1 by 4 pi epsilon naught, and of course p cap as it is. Now this is the net electric field. Now further, in the beginning I told you what is the dipole moment p. Dipole moment p is 2q into a, that is magnitude of one of the charges q into the length of the dipole 2a. So 2 into qa is the dipole moment, which is denoted by capital P. So capital P I will just substitute here for 2qa. So 1 2 will be left out. So 4qa is nothing but 2 into dipole moment, that is 2p. So let me just put that here. So therefore the net electric field due to an electric dipole at a point on the axial line is 1 by 4 pi epsilon naught into 2p by r cube into p cap, where what is p here? P is equal to 2 into qa, which is the dipole moment. It is the dipole moment. So that's the electric field of an electric dipole. E on axial line. So electric field of a dipole on the axial line. So I hope that is clear. So electric field on the axial line we found out. So that's a dipole. Along the line we considered a point. At that point we found the electric fields E plus Q and E minus Q individually due to plus Q and minus Q of the dipole. And then after finding E plus Q and E minus Q, we added them vectorially to get the resultant field at P, which is E is equal to so much, where P is the dipole moment. And of course epsilon naught already you know, which is the absolute permittivity of free space. So that's the first case. Now let us move to the second case. Let me remove this.